Dear all, good morning. In the last lecture, we discussed properties of eigenvalues. In that lecture, also we discussed eigenvalues of idempotent matrix, involuntary, and nilpotent matrix. Those matrices also we can say special matrices. In this lecture, we are going to discuss some more special matrices, eigenvalues, and complex matrices, eigenvalues. We'll see. First up, the eigenvalues of a symmetric matrix are always real numbers. The proof is simple. The eigenvalues of symmetric matrix. Already know symmetric matrix means A is a real matrix. Any real matrix, n by n matrix. Symmetric means transpose equal to A. When that a matrix is symmetric matrix, the eigenvalues is always real numbers. Maybe the eigenvalues real or complex. In last class we discussed one. We find out the matrix eigenvalues. Real matrix we are getting complex numbers. Eigenvalue. That means eigenvalues are real or complex, but if matrix is symmetric matrix, in that case, eigenvalues are always real numbers. It's simple. Let A be a symmetric matrix. Symmetric matrix. Matrix and lambda be an eigenvalue of a corresponding eigenvector x. Yeah, that is Ax equal to lambda x. We'll take this equation is 1. Now conjugate transpose. Take in conjugate transpose. So we get conjugate transpose. Conjugate transpose we are denoting x star. Suppose conjugate a conjugate A transpose. We are writing a star. Present. Conjugate transpose means okay, means x star lambda x star. This implies a star. That means x star a star is equal to lambda is a number. Conjugate transpose is same. Conjugate means lambda bar. Conjugate x star. So, yeah, this is lambda bar x. Now, okay. So now, what is a square matrix? Real and square matrix. This one x star a conjugate transpose. This you can say A into lambda bar x star. You can write since A is symmetric matrix. Real symmetric matrix. Yeah, when the real A conjugate is same as A and transpose A conjugate transpose same as also A transpose. A transpose same as the that's why x star A is equal to lambda matrix. Now post multiply with x. That means x star transpose x equal to lambda bar x transpose x. Let's take second equation. Post multiply. Now multiply x, multiply equation 1 with x, we get multiply with x star, the conjugate transpose. When we are multiply with x star, we get x star x equal to lambda x. Lambda you can write scalar, you can outside x star second third equation. Second and third, the LHS is same, that means RHS. From second and third, this LHS same, RHS equal to means lambda x star x equal to lambda star x star x. That implies lambda minus lambda conjugate into x star x equal to 0. But here x is means like some x1, x2, xn. X conjugate transpose means x1 conjugate, x2 conjugate, and so on, like this one, xn conjugate. When you take this x conjugate transpose, that means x star. Well, x star into x. When you x star into x, if you multiply this both, you will get x1 conjugate into x1, x1 conjugate into x2, and so on. Xn conjugate into xn. That means mod x1 square, mod x2 square, and so on, mod xn square. Mod xn square. This is all positive, but the eigenvectors are non-zero. At least one of the coordinate is non-zero. If x1 is non-zero, this term is must be non-zero. It means it's not equal to 0. It means it's more than not equal to 0, and it's more than 0. It's greater than 0. That's why this is greater than 0 means non-zero. That implies lambda minus lambda bar equal to 0. Since x star x not equal to 0. That implies lambda equal to lambda bar. What the lambda equal to lambda bar? We are taking lambda is eigenvalue of a matrix lambda bar. When it's possible, means therefore it's a real. A number and conjugate both are same means real. Therefore lambda real. Hence eigenvalue of a symmetric matrix are real numbers. You can write. Hence we write one more step. Hence eigenvalues of a symmetric matrix are real. Yeah, this is the proof. That means eigenvalues of a symmetric matrix always real numbers. Next another theorem. The eigenvectors correspond to distinct eigenvalues of a symmetric matrix are orthogonal. Orthogonal means that inner product of x1 comma x is 0, or you can write x1 transpose x2 is 0. You have to prove. That means they are orthogonal. The eigenvector corresponding to two distinct eigenvalues of a symmetric matrix. Not every matrix. For a symmetric matrix, eigenvectors are orthogonal. See proof. Last class we discussed eigenvectors corresponding distinct eigenvalues are linearly independent eigenvectors. Linearly independent. For eigenvector corresponding to symmetric matrix with distinct eigenvalues, they are orthogonal. Suppose let x1 and x2 be two eigenvectors of a symmetric matrix A, and corresponding corresponding distinct eigenvalues lambda 1 and lambda 2. Yeah, that is x1 equal to lambda 1 x1 and x2 equal to lambda 2 x2. This is the one. Now take any one. Suppose take this one. X1 equal to lambda 1 x1 Now multiply with x2 transpose. Multiply x2 transpose. Okay, right. Multiply. Okay. Multiply x1 minus lambda 1 x1 with x1 transpose. 2 transpose. Yeah, we get that means transpose x1 equal to lambda 1 x1 x2 transpose. Now take both transpose. Take transpose. That means x2 transpose x1 transpose is equal to lambda 1 x1 x2 total transpose of transpose. This implies that means so like a plus b c transpose equal to reverse. That means we get x1 transpose a transpose 2 transpose whole transpose equal to lambda 1 transpose is same. Lambda 1 is a number you can write first. x2 transpose whole transpose into x1 transpose. That implies x1 transpose a transpose. A is a symmetric matrix. Transpose is same as the A. x2 transpose whole transpose. That is x2 equal to lambda 1 x2 transpose the same x2 x1 transpose. Hence we can write since A transpose equal to A is a symmetric matrix. Suppose take this is the equation is 1. x1 transpose ax2. Now pre-multiply the second equation. Pre-multiply x2 equal to lambda 2 x2 with x1 transpose. We get whenever pre-multiply with x1 we get x1 transpose ax2 equal to lambda 2. You can write scalar. You can write multiply means that means x1. Any mistake? Sorry. Here we are pre-multiplying. Sorry. Pre-multiplying. Pre-multiplying means lambda 1 x2 transpose x2 transpose x1. That means x2 transpose x1. I mean we will get lambda 1 x1 transpose x2 transpose whole transpose. That means x1 transpose x2 x2. So now we are multiply x1 transpose this one x1 transpose x2. So check 1 and 2 left hand side is same. Now right hand from 1 and 2 from 1 and 2 lambda 1 x1 transpose x2 equal to lambda 2 x1 transpose x2. This implies lambda 1 minus lambda 2 x1 transpose x2 equal to 0. But these are distinct values. Distinct values means lambda 1 minus lambda 2 and 0. That implies x1 transpose x2 equal to 0. Since lambda 1 not equal to lambda 2. Yeah, that means x1 transpose x2 is 0 means they are orthogonal. Therefore, x1 and x2 are orthogonal. Hence, eigenvectors corresponding to distinct eigenvalues of a symmetric matrix are orthogonal. Any distinct one. Now we can observe. Last class we discussed the eigenvalues and eigenvectors of this 1 1 1 1. The symmetric matrix. Now we got eigenvalues are 0 0 0 0 3. Now we can check 0 0 3. Corresponding 0 we got two eigenvalues, eigenvectors, not orthogonal. Now corresponding each one eigenvector and corresponding three eigenvectors that are orthogonal. Thus, they are linearly independent eigenvector but not orthogonal. Corresponding 0 to 3, corresponding 0 we got two eigenvectors x1 and x2. And corresponding 3 x3 means x1 transpose x3 is 0 and x2 transpose x3 also 0. But x1 transpose x2 is not 0. But x1 x2 transpose not equal to 0 because corresponding same eigenvalue x1 transpose x2 is the corresponding same eigenvalue. They are not orthogonal. But corresponding to different eigenvalues is orthogonal. Yeah, these are orthogonal. x1 x3 and x2 x3 are orthogonal, but x1 x2 not orthogonal. They are linearly independent. 3 are linearly independent. Check it this one. It means corresponding symmetric matrix with the distinct eigenvalues. They are orthogonal vectors. Now another one. The eigenvalues of a skew symmetric matrix are 0 or purely imaginary. Skew symmetric means skew symmetric means transpose equal to minus a. If I give idea, same procedure, any vector eigenvalue, that means ax equal to lambda x. We are taking a is the skew symmetric. Now multiply with x conjugate transpose. X conjugate transpose x equal to lambda x conjugate transpose x. Same as you can write x star x equal to lambda x star x. Now if you take this one, suppose take this equation 1. Now take conjugate transpose. Suppose take x transpose x star lambda x star whole star. This implies we will get x star. A star is a two-year emission. That means we get minus a here. As it is real, conjugate is same. That means we will get x star of x star. That x is equal to lambda into x star on x. The same as you can write x star ax equal to minus lambda x star x. Let's take 1 and 2. From 1 and 2, the left hand side is same. That means we get lambda x star x equal to minus lambda, sorry, conjugate transpose. That means conjugate. That means we get lambda bar x star x. That implies lambda minus lambda bar. If you write it as x star of x, we know this is a non-zero vector. That means lambda plus lambda bar equal to 0. That is lambda equal to minus lambda bar. It's possible lambda equal to lambda bar. When it's possible lambda equal to lambda bar, it is possible when lambda is 0 or purely imaginary. Purely imaginary means imaginary number. Yeah, therefore, we are taking as the skew symmetric matrix. Therefore, eigenvalues of a skew symmetric matrix are 0 or purely imaginary. It's not real. If the matrix is skew symmetric, it's not a real matrix. This is the one. Purely imaginary. Now take this is the one. Go for same proof for first one. We'll get it. Next, the eigenvalues of orthogonal matrix are -1 or 1. See, we know this eigenvalue. Same thing. X equal to lambda x. Orthogonal matrix means so A transpose A equal to A transpose equal to identity. You know this one. Now x equal to lambda x. Suppose you go for transpose. Suppose free multiply A transpose x equal to lambda A transpose X. This implies A transpose A is the identity X. I into X equal to lambda A transpose X. Same as A transpose X equal to okay transpose X 1 by lambda X. Okay, we'll go for another way also. Okay, but we have to know that says yeah, orthogonal matrix is non-singular matrix. Direct you can write that one, but we put this one. Yeah, we have to put the eigenvalue. Yeah, I'll give this region later. Okay, now A transpose X is equal to this lambda I into X equal to lambda. We know eigenvalues of A and A transpose both are same. That means lambda into A transpose eigenvalues you can write lambda into X. Since eigenvalues of you know this one A and A transpose are same. Lambda is eigenvalue of A, and also eigenvalues of A transpose also. That implies 1 minus lambda square X equal to 0. Eigenvector is a non-zero. Therefore, 1 minus lambda square equal to 0. Since X is non-zero, that implies lambda equal to or minus 1. It means minus 1 or 1. Now, you can remember one more thing. Suppose if the orthogonal matrix is a singular matrix, lambda is eigenvalue of A, then the reciprocal also eigenvalue. Then 1 by lambda is eigenvalue of A. A is orthogonal matrix. Better to write eigenvalue of orthogonal matrix. Eigenvalue of orthogonal matrix. Okay. Then 1 by lambda is eigenvalue of orthogonal matrix A. Orthogonal matrix because 1 minus 1 eigenvalue, that 1 by 1 also eigenvalue, minus 1 minus of 1 minus 1 is eigenvalue. If you take 1 by minus 1, again it's a minus 1. But if eigenvalue of lambda is eigenvalue of a orthogonal matrix A, then the reciprocal also eigenvalue of orthogonal matrix A. Reciprocal means only eigenvalues are minus 1. The reciprocal of 1 is 1, minus 1 is 1. That means the eigenvalues of orthogonal matrix are plus or minus 1. 1 or minus 1. Now complex matrices. We know already we discussed complex matrices. Three types of complex matrices: Hermitian, square Hermitian, and unitary matrix. We'll see first Hermitian matrix. The eigenvalue of a Hermitian matrix are always real numbers. Same proof. Hermitian matrix means we know A star equal to A. Now we go for the proof. When you write A star A, now take eigenvector. We are generally taking X equal to lambda X. Now take conjugate. X conjugate X equal to lambda X conjugate X. This one. Now take conjugate transpose. That means for this one, conjugate transpose. X transpose AX lambda X star A. X conjugate. Now whenever I take this one, X star A star equal to A. That is A. X star of X this is equal to lambda conjugate. Transpose is lambda bar. Means X star of X will get. From 1 and 2, this left side is same, right side will get lambda minus lambda bar into X star into X. Like same proof first one. Means this is non-zero 1. It means lambda equal to lambda bar. When it's possible, that's a real. It means eigenvalues of Hermitian matrix always real numbers. Same proof you can write. But the eigenvalues of a square Hermitian matrix are purely imaginary or zero. Same proof. In place of this proof, yeah, we are getting a conjugate equal to minus a. We get minus a means we get here lambda plus lambda bar equal x star x equal to 0. Means we get lambda conjugate equal to minus lambda. This is possible when is the lambda is 0 and purely imaginary. Purely imaginary. That means eigenvalues of two Hermitian matrix are purely imaginary or 0. Okay, this one. Next unitary. The eigenvalues of on unitary matrix have absolute value 1. Unitary matrix means we know A is a matrix. Unitary matrix means A star A star equal to identity. We know this one. Suppose lambda is eigenvalue corresponding eigenvector x. Suppose lambda is eigenvalue of A corresponding eigenvector x. This means Ax equal to lambda x. Suppose take this is a one equation. Suppose not write same way write this one. Suppose now a conjugate transpose. That means conjugate transpose x star equal to lambda x star. That implies x star a star equal to lambda conjugate x star. Now multiply this one and 2. 1 and 2. What are 1 and 2? If you multiply this one, x transpose a star into x. Now right side lambda bar into lambda x star into x equal to what is a star a? A star a equal to I identity. Means we get x star into x equal to lambda bar into lambda. We can write mod lambda square into x star into x. This implies lambda bar square minus 1 into x star x equal to 0. This is non-zero value. That implies mod lambda square equal to 1. That means absolute value. That implies mod lambda equal to 1. Yeah, lambda square is 1, mod lambda also 1. That means the absolute value is 1 for unitary matrix. So this is the location of eigenvalues of Hermitian, square Hermitian and unitary. See, we know square Hermitian for real matrix is symmetric. Unitary matrix real matrix is orthogonal. Hermitian matrix is real is symmetric. But take lambda is a real, this is a real line, this is the imaginary one. Now eigenvalues of Hermitian and symmetric always on real line. That means we get eigenvalues always on real line. So let's say square Hermitian or skew symmetric. The eigenvalues are 0 and purely imaginary. The eigenvalues lies on imaginary line, or maybe 0 also on imaginary line. 0 or imaginary. Now orthogonal matrix are we get orthogonal eigenvalues are -1, -1 or 1. What the absolute value of lambda is 1. That means unitary and orthogonal matrix absolute value is 1. That is unit circle. Radius is 1. The location. Now we'll see some problem. Find the eigenvalues and corresponding eigenvectors of the following matrix. Suppose take this first one. Let A equal to 4, 1 minus 3i, 1 plus 3i, 7. Now this is a star equal to A conjugate transpose, Hermitian matrix. Hermitian matrix. I'm not finding the real matrix. Already we know how to find the real matrix eigenvalues and eigenvectors. This is the Hermitian matrix. What the eigenvalues of Hermitian matrix are? Real. Now we'll see we get real or not. Now first characteristic equation. Characteristic equation of A is determinant of A minus lambda is equal to 0. That implies 4 minus lambda, 1 minus 3i, 1 plus 3i, 7 minus lambda equal to 0. That implies 4 minus lambda into 7 minus lambda equal to minus 1 minus 3i into 1 plus 3i equal to 0. Now simplify this one. Lambda square 7 minus lambda 7 plus 4 minus 11 lambda minus 28 minus a plus b into a minus b, a square minus b square 1 b square I square 9 I square is minus 9 equal to 0. That implies lambda square minus 11 lambda plus 8 minus 18 equal to 0. Now this one you can write lambda minus 2 into lambda minus 9. Therefore lambda equal to 2 comma 9. Therefore eigenvalues of A are 2 and 2 eigenvalues. Now find eigenvector corresponding to 2 and 9. Vector corresponding lambda equal to, that means a minus 2i x equal to 0. That implies a minus 2i. A is the 4 minus, this is 2i. Minus 2, 1 minus 1 minus 3i, 1 plus 3i, 1 minus 2, 5 into some x1, x2 equal to 0. That implies apply operation 2 1 minus 3i. Now you convert to 0 x1 x2. So what we require r2 2 r2 minus 1 plus 3i r1 0 r2, that means 10 minus 1 plus 3i into 1 minus 3i, 1 plus 3i into 1 minus 1 plus 10, 1 plus 9 minus 10 is also 0. That implies 2x1 plus 1 minus 3i x2 equal to 0, same as x1 equal to minus 1 minus 3i x equal to by 2 x equal to 0. Therefore x equal to x1 x2. x1 you can write minus 1 minus 3i divided by 2 x2 x2. This is equal to x2 into minus 1 minus 3i. By 2 also you can take common if write 2. Okay, I write x2 minus of 1 minus 3i by 2 1. Or you can write the same as if you write x2 by 2 common, this is minus of 1 minus 3i by, but if it is a vector, the scalar multiple also vector because it's a linearly independent. And x2 belongs to any real number. It's minus of 1 minus 3i, or you can write minus 1 minus 3i by 2 1 is eigenvector of a corresponding lambda equal to 2. Similarly, second one, find eigenvector corresponding. Similarly, find eigenvector corresponding lambda equal to 2. Find similarly lambda equal to 9 7 2 comma 9 9 9. Now you can check it. The trace is 1 plus 4, 11. 9 plus 2, 11. Now you can say determinant must be 18. 28 minus 10, 18 will get. Now we will see the second one. Now observe here, this is the diagonal elements are purely imaginary, and this is skew Hermitian matrix. Now let A equal to what the matrix 3i 2 plus I minus 2 plus I minus I. This is the matrix. Now we'll see find the eigenvalues. Second problem. Solution. Now find this skew Hermitian matrix. Hermitian matrix. What are the eigenvalues? Must be 0 or purely imaginary. Now we'll see. Find a characteristic equation. Is a minus lambda is equal to 0. Now a minus lambda is 0. Now find it. This equal that implies 3i minus lambda 2 plus I minus 2 plus I minus lambda. Determinant equal to 0. That implies 3i minus lambda into minus I minus lambda minus 2 plus I into minus 2 plus I. 0. So, this implies lambda square 3i minus 3i lambda plus I lambda minus 3i lambda, correct? Minus lambda plus lambda minus 3i minus 2i lambda I into minus I minus 3i square 3 minus a plus b into a minus b I square minus 1 minus 0. That means lambda square minus 2i lambda plus 5 plus 3 8 plus 8 equal to 0. Now find these values. Now find these roots. Now you can use any method roots. This one you can write lambda minus 4i lambda plus 5. You can take it. Or you can use this one, or lambda equal to minus b 2i plus or minus b square I square minus 4 minus 4ac minus 8 by 2. It means 2i plus or minus 12. 4ac 4ac 32 36, that's just 6i by 2. It means we can to cancel, that is I plus or minus 3i. If you take 4i minus, that implies lambda equal to minus 2i comma 4i. The eigenvalues of AR minus 2i and 4i. And eigenvector corresponding this one, same procedure, and eigenvectors. Vectors corresponding these eigenvalues. These eigenvalues. Let we will see another example. For example, find eigenvalues and eigenvectors of I 0 0 0 0 I 0 I 0. Already this is a unitary matrix. Already we checked this one when we discussed the complex matrices and eigenvalues and eigenvectors of this one. This is solution. Let A equal to I 0 0 0 0 I. It's not mentioned it's this unitary or whatever matrix. Even though this is unitary, square mission also this one. The eigenvalues are 0 purely imaginary or that absolute value is 1. Not to be that one. It's a unitary matrix. Better to now write characteristic equation. Equation of A is element of A minus lambda I, sorry, lambda capital I equal to 0. Implies I minus lambda 0 0 0 0 minus lambda I 0 I 0 minus lambda equal to find determinant. You can go, yeah, only one is that go for any row or first column. I minus lambda into, if we remove first row and first column, this is minus lambda into minus lambda square minus I square. That's what. That implies lambda equal to I or lambda square, that's 1 equal to 0. That implies lambda equal to I or lambda equal to plus or minus I. Therefore, eigenvalues of A or minus I, eigenvalue. So, minus I comma I, this one. Now find eigenvector corresponding to these eigenvalues. Eigenvector corresponding lambda equal to, okay, this is a repeated one. We'll see. Eigenvector corresponding to lambda equal to I. Okay, find this one, lambda equal to I. That means you get A minus lambda. Corresponding to this one, we get two eigenvectors. And corresponding minus I, we get another eigenvector. This one, okay, pressure. Now I stop here. Thank you.